Let's harken back to Calculus 1 when we were learning to use calculus to analyze graphs. And, we had situations like this where we would have a graph, it's increasing here, then decreasing, maybe doing something like that. And this is the graph of f of x. And we learned this, that we could determine if a graph was increasing by studying the first derivative. And you can see these tangents here are all positive. The first derivative is positive. And notice that these tangents, though, they're getting less and less steep. See? Notice this first tangent is steeper than the second and so forth. And these things are kind of flattening out. In other words, yeah, the first derivative is positive, but it's decreasing. The slopes of those tangents are getting smaller and smaller. So we talk about the second derivative, which is a measure of the rate of change of the first derivative, and it's less than 0. And notice that that corresponds to a graph being concave down. This graph here is concave down over this part, that we just measured over this part here. And at some point it turns concave up, but here it's concave down. Now let's look over here at where the graph is concave up, and notice that if you look at the tangents here, they're getting more and more steep. So here we have the first derivative is positive, but also the second derivative is positive because it's measuring the rate of change of the first derivative, and the first derivative is increasing. And that corresponds to concave up. So over here we've got concave up, and at some point here we have an inflection. Okay, so we have concave down, concave up. Now, we use this whole thing of concavity, to help us identify maxes and mins in a graph. So notice, let's suppose that this point up here is a critical point. It's where the tangent is horizontal. Notice the graph is concave down there. And we said that if you plug in to the second derivative and you get a negative, that indicates that your graph is concave down there, which would help you to see, I'm at a maximum because I'm on top of this thing that's opening downward. Let's harken back to Calculus 1 when we were learning to use calculus to analyze graphs. And we plug in we had situations like this where we would have a graph x1, and that's greater than 0. Increasing here. Well, that means you have concave up, or in other words, doing something if that's like a critical point there. And you're at a minimum graph of f of x. And we learned this, that so we could use the second derivative for that. We could determine if a graph was increasing by studying the first derivative. That is called the second derivative test. And you can see these tangents here. Now think about positive. Another situation. The first derivative is that you have a graph positive. It has a horizontal tangent. Notice that these tangents, though, let's suppose this is a horizontal, they're getting less and less steep. See? And notice it kind of flattens out. Is steeper than the second. So what we have here is we have things are kind of flattening out. Equal to 0. In other words, yeah, the first derivative is positive. I've got a critical point, but then if we plug in the f double prime, the slopes of those tangents are 0 as well, getting smaller and smaller. In other words, cases like that come up. We talk about the second derivative equaling 0, which is a measure of the rate of change of the first derivative, and it's whether or not you've got a maximum or a minimum. And notice that corresponds the second derivative test is not going to apply. This graph here is concave down. So there's some background, that we just measured over this part. Now, what I want to do is I want to talk about this second derivative test for multivariable functions, and where the graph is concave up now. And notice the second partials test here. Now, before we do that, they're getting more and more steep. So here, briefly, we have the first derivative is positive, but also the second derivative is positive. F of x, because it's measuring the rate of change of the first derivative, and the first derivative is increasing. Plus c. And that corresponds to concave up. So over here, we've got a basic function here that we've studied here. We have an algebra 1. But let's think about this function. So we have concave down, concave up. Now, consider if we want to find this whole thing of concavity zeros to help us identify, we know how to do mins in a graph. So notice, let's suppose that this and point up
in
here
particular,
is a critical
we have
point.
a
It's
formula
where
for that. We have the
the quadratic formula.
tangent is
Negative b
horizontal.
plus or minus the square root of b
Notice the
squared
graph
minus
is concave
4ac
down there.
all over 2a.
And we said
Everybody
that
knows
if you
this.
plug in to the
Now,
second derivative
I want to
zero in
and you get a
on what's
negative
under this radical.
that indicates that your
I'm gonna
graph is
zero in on
concave
that.
down there, which would
And
help you
think
to see,
about this.
I'm
B
at a
squared minus
maximum
4ac.
because I'm on front of this thing, I'm on
Okay.
top of this thing that's opening downward.
And I want to
Likewise, let's suppose down here
consider
we
what
have
happens
a critical
if
point.
b squared minus
x1 y1
4ac is less than 0.
and we plug in here
Okay, let's
and we
suppose
have
this is
x
less than
double
0.
prime of x1.
Well, if
And that's
that
greater than 0.
radicand is
So that
less than
means you have
0, then that
concave up,
means
or
there are no
in other words,
real
if that's a critical
intercepts.
point
There are no
x-intercepts.
You're at a minimum.
There are no real roots.
And in fact,
so we could use
if you
the
have a
second derivative
situation
for
like
that.
this, you have a couple of
Now,
options.
that
here's
is
one.
called the second
The
derivative
graph
test.
might
That's what we
open
called
like
it.
this.
Now think about another situation. Let's
where it doesn't
suppose
cross the
that you have a
x-axis,
graph, or
it has
might
a horizontal tangent here.
be underneath like this.
Let's suppose
and open
this
down.
is a horizontal tangent.
Okay. So
And
if b squared minus
it kind of
4ac is
flattens
less than
out.
0, so what we have here is
And
we have
if
f
A
prime is equal to
is
0.
greater than 0,
In
okay,
other words, if
which
a
would
is
indicate
positive,
I've got a
the
critical
coefficient of the x
point.
squared is positive.
But then if
it's
we
going to
plug
be
in
like
the f
this.
double
In other words,
prime,
the function
we
is
get
all
0
positive.
as well.
It's all above the axis.
In other words,
cases
however,
like that come
if
up.
A is less
And
than
if you
0,
get the second
then we have
derivative
something
equaling
below
0,
the axis,
then that
and
tells
that
you nothing
the graph
about
is all in
whether
the
or not
negative
you've got a
values.
maximum or a minimum. In other words, this second derivative
Now,
test
just
is
for
not going to
terminology,
apply.
let's remember
Okay,
what this is
so
called.
there's some background.
This right here,
This is called the discriminant.
now what I want to do is I want to talk about this second derivative test for multivariable functions.
Okay.
That's what we're going to look
So
at
if I
now.
say the discriminant,
The
you'll know
second
what I'm talking
partials
about.
test.
Okay,
Now,
before we do
that's
that,
if
I
b squared
want
minus
to
4ac is less than
just
0. Now
briefly
let's
talk
think about, well, what happens
a
if it's
function
greater
like
than
this.
0?
So
F of
let's
x
think about what would happen if b
equals
squared minus
ax
4ac
squared plus
is
bx
greater than 0.
plus c.
Now you're thinking, well,
Well,
this is
if b squared minus
this is just a
4ac
basic function here that we've studied
is
in
greater than
algebra
0,
1. Then we have something.
but let's
you know,
think
that
about
looks
this
like
this
this.
function
In other
here.
words, we have two roots.
Consider
And it
if
doesn't
we
have
want
to
to
look like
find
that. It could
the
it could be
zeros of
opening
this
down.
function.
But
Well,
the
we know
point
how to
is
do that.
we
We've
have
got
a
ax
couple of
squared
roots.
plus bx
And
plus
here's what I
c
want to point out.
equals 0.
And
For some
in
parts of this,
particular,
the graph
we
is
have a
positive,
formula
and for
that.
some
We have
parts
the
it's negative
quadratic
on
formula.
both of these.
Negative
Here
b
it's
plus or minus
positive,
the square
and
root
here
of
it's
b
negative.
squared minus 4ac.
That's the important thing to remember
over
about
2a.
that. It's not
Everybody
always
knows
positive,
this.
it's not always negative.
Now,
Versus what
I
we had
want
up here,
to
b squared minus
zero
4ac,
in
it's
on
either
what's
all
under this
positive or
radical.
all negative. It never
I want to
crosses the
zero
axis.
in on that.
Now,
And
let's look
think
at
about
this.
the
b
last
squared
case.
minus 4ac.
Let's say that b squared minus 4ac is actually equal to
And I
0.
want to
Well, if that's
consider
the case, you
what
have a situation
happens
like this.
if b
You
squared
have
minus
the
4ac
graph
is less than
kind of
0.
bounces off like
Okay,
that.
let's suppose
It
this
either
is
looks
less
like
than
that
0.
or,
Well,
like
if
this.
that radicand
So
is
those are the
less than
cases
0,
that we
then that means
just
there
to
are
refresh
no
your memory
real
when we're talking about
intercepts.
quadratic
There are no
x-intercepts.
functions,
There are
quadratic
no real
equations.
those
Those
are
are the
roots.
cases.
And
we
in
have.
fact,
If you have
now
a situation like this, you have a
I
couple
want
of
to
options.
go now to the
Here's one.
multivariable
graph
and talk about the
might open
discriminant
like this.
in multivariable for the second partials test,
where it doesn't cross the
So we'll look at that
x-axis.
now.
Or
It
let's
might
suppose
that
we
be
have
underneath
a
like
function
this
here.
and open down.
Okay.
So I have f of x,
Okay.
y.
So if b squared minus 4ac is less than
equals,
0,
well, let's just do
and
this. Z
if
equals f of
a
x, y. That's all
is
we
greater
need.
than 0, in other
Okay.
words, if a is positive,
And what I
the
want to
coefficient of
do,
the x squared is positive, it's
I
going to be
want
like this.
to
In other words, the function is
find
all
the
positive.
second
It's all
directional
above the axis.
derivative. In
However,
other words, I want to
if a
find a
is less
directional
than
derivative,
0,
and let's say
then
it's
we
in
have
the
something
direction
below the
of
axis, and that
the graph is
AB.
all in the negative values.
And let's suppose that this u
Now,
is
just
a
for
unit vector.
terminology, let's
Okay?
so
Remember
I want
what
the
this is
directional
called.
derivative in
This
that
right here,
direction.
this is
right
called
there.
the discriminant. And I want to do it twice. In other words, what I want to find is I want to find the directional
Discriminant.
derivative of the
Okay.
directional derivative.
So if I say the discriminant, you'll know
in
what
other
I'm
words,
talking about.
I'm looking at
Okay,
concavity,
now, And
That's if b
concavity
squared minus 4ac is
is,
less than
we
0.
studied that with the
Now
second
let's think
derivative.
about,
So
well, what
let's get at it
happens
here.
if
Let's
it's
see if we
greater
can
than
figure out
0.
what this is.
So let's
So
think about
first
what
of
would
all,
happen if b
the
squared
directional
minus
derivative.
4ac is greater than 0.
Let's see what we've got. We've got
Well, if b
the
squared minus
partial with respect
4ac
to x
is
a
greater than 0,
plus the
then we
partial
have
with
something,
respect to y,
that looks
b.
like this. In other words, we have two roots.
Remember, that's how we
And
find the
it
directional
doesn't have
derivative.
to look like that. It could, it could be opening
Okay.
down. But the
So
point
it's
is,
in the direction of
we
AB.
have a couple
Now,
roots.
I want to go
and
back
here's what I want to point
and
out.
find the directional derivative.
For some parts of this,
that
the graph
in
is
the same
positive,
direction
and
of
for some
AB.
parts, it's negative.
Okay.
On both of these. Here it's positive.
Okay, so here
and
we
here
go.
it's negative.
Here's
That's the
the
important
next
thing
part.
to remember about that.
The
It's not
directional
always
derivative
positive, it's not always negative.
of the directional
Versus
derivative.
what we had up here, b squared minus 4ac, it's either
Okay.
all positive
So
or
here I
all
go.
negative. It
Here's
never
my
crosses
function
the
now.
axis. I've got to take the
Now,
derivative
let's look
of
at
this
with
the last
respect
case.
to x.
Let's say that b squared minus
Okay.
4ac
So that's going to be the
is
first
actually
term.
equal to 0. Well, if that's the
Times
case, you
A,
have a situation
right?
like this. You have
And
the
then
graph
the derivative
kind of
of this
bounces
with
off
respect to x
like that. It either looks like
times A.
that,
Okay.
or so there's the first
like
part.
this.
This is the
So
derivative.
those are
of,
the cases that we
x times
just to refresh your memory when we're talking about quadratic.
Plus, now I'm ready to do the
functions,
y. Quadratic
so
equations.
I take
Those
the
are the
derivative,
cases we have.
Okay, with respect to
Now,
y.
I want to
Multiply
go
it by
now
b.
to the multivariable and talk about the discriminant
There we go.
in multivariable
is.
for the second partials test. So we'll look at that now.
So
there is the directional derivative
let's
of the directional
suppose
derivative in the
that
direction
we have
of AB.
a function here.
Now,
Okay,
I
so
want to
have
point out
f of
something
x,
here.
y
Notice that these two
equals,
are like terms.
well, let's just do this.
The
Z
partial,
equals f of x, y. That's all we want
yx
to
is
do.
the same as xy.
Okay.
So let's
And what I
just
want to
rewrite
do,
this, see if we can
I want
clean it
to
up a little bit. Here we have
find
x,
the
f
second
directional
x,
derivative.
a squared.
In other words, I want to find a
Plus
directional derivative, and let's say it's in the
f
direction
xy
of
AB.
AB. And then
And
finally,
let's suppose that
this
y
u is a unit
b
vector.
squared,
Okay,
like that.
so I want the directional derivative in that
Okay.
direction right there.
Now,
Here's what I want to do,
and
and I want to do it twice.
I'm
In
going
other words,
to
what I want to find
do a little trick here.
is I want to find,
And you'll see why
the
in just a
directional
second, but
derivative
I'm
of
going
the
to factor
directional
out this b
derivative.
squared. Okay.
In other words,
So here I go.
I'm
going to
looking at
factor out a b
concavity,
squared. Just put it
and
on
concavity is, we studied that
and
with
now
the second
I
derivative.
get
So
this.
let's get
I
at
get
it. Here,
f
let's see if we can
x
figure out what this
x
is.
a
So first of
squared
all,
over
the
b
directional
squared.
derivative, see, compensating for the b squared that
Let's
was
see
factored
what we've
out.
got.
Plus,
We've got
the
2.
partial with respect to x.
I've got,
if you look here, this is going to be
plus
2
the partial with respect to
a
y
b.
uh,
Remember,
over
that's
b.
that's how we find the directional
2a over b.
derivative. Okay. So it's in the direction of AB.
fxy.
Now I want to go back
Okay.
and find the directional derivative.
Now think about it. If I
derivative of
multiply through by
that
b
in the
squared, I
same
get
direction of
here.
AB. And
Okay.
then finally, f.
Okay, so here we go.
Here's
like
the
this.
next part. So the directional derivative
Okay,
of
here we go.
the directional derivative. Okay.
Now,
so here I go.
Here's my function now.
Do this to make this a little bit
derivative
of this with respect.
I'm
going to do
x.
this to make it a little bit clearer what we're trying to do. So
I'm
that's
gonna
going to be
let
the first term. T
times
equal
a,
right?
over b.
And
And
then
dig
the
what we have
derivative
now.
of
If we
this
do
with
that, we've
respect
got
to
b
x
squared
times a.
That's still
Okay.
there.
So there's
And
the
then
first
we've
part.
got
This is
f
the derivative
x,
of
x
with respect to x
t
times
squared
the x coordinate.
plus
Now I'm ready to do
fxy
the y.
t.
So I take the
plus
derivative
fy.
okay, with respect to y. Multiply it by b. Now I'm going to just work
There we
with
go.
this part in here.
There it is.
From now on, because
So
b squared
there
is the
is
directional
there.
derivative of the
It's
directional
always
derivative in the
positive
direction of AB
because it's squared.
Now I want to
And what I'm
point
wanting
out
to be
something
concerned
here.
about is the
Notice
signs,
that
positive
these
or negative.
two
So
are like
going
terms.
forward,
I'm just going to ignore this
partial,
b squared and just
yx
focus
is
in
the same
on
as xy.
the
So
inside here. Let's just rewrite this.
now,
See if we
if
can
you think about it,
clean it up a little bit.
this is
Here
a
we
lot
have
like
x,
a quadratic
a quadratic function here. Notice
plus
we have
2 f
t
x
squared
y
plus
ab
b
and
t
then finally
plus
f
c. You could
y
think of it that
y
way, right? Where a
t
is fx
squared like
x
that.
and b is 2f
Okay.
xy,
Now,
here's what I want to
and
do.
then you have the constant on the
I'm
end. So
going
it's
to
it's kind of like
do a
that.
little trick here, and you'll see
Now,
why in just a
I'm going
second,
to
but I'm
find the
going to factor
discriminant.
out this b squared. Remember, it's b
Okay.
squared
So
minus
here I go. I'm going to
4ac.
factor out a b
So
squared.
let's
Just
think
put it
about
on
this.
the
b squared,
outside.
that's going to be 4
And
f
now I get
x
this.
y
I get
squared.
f x
See, that's b
x
squared. That's
a
this
squared over b
minus
squared. See,
4
compensating
a
for the b squared that was
c
factored out.
plus 2.
Now, I've got, if you look
Okay,
here, this
there it
is going
is.
to be
So
2
now I've got b squared minus
a
4ac.
uh,
Now, let's
over
start
b,
playing the game with this that we did
2a
with
over
the
b.
discriminant on the quadratic.
Okay.
And let's remember, this is the part that would be under the radical.
fxy.
And we want to say, okay, what happens
Okay.
if this thing is
Now
negative?
think about it. If I multiply through
Let's
by
think
b
about what
squared, I get
happens if
ab
this is
there.
negative. Now,
And then
I've got these
finally,
forals on here, which I
f
don't care for. So let me just
yy
divide
like
them out.
this.
And what I'm looking at is fxy
Okay, here we go.
squared minus fxx. Now,
fyy.
I'm gonna
Okay.
do
So I
this to make
divided
this
out
a
that
little
4.
bit.
Just makes it a little simpler.
I'm going to do this to make it a little bit
If that
clearer
right
what we're
there
trying to
is
do.
negative,
I'm going to let, now remember, this is measuring the
t
concavity. This is measuring the
equal a
concavity.
over b.
So let's think about what that
And then
means.
dig what we have now.
That
To do that, we've
means
got b squared
that you have a situation
that's still
like
there
this, and then we've got
because there's no
fxx
real roots.
t
Squared
or you have a situation
plus
like this,
2
fxy t
yeah,
plus
you have one of those
fyy.
two.
In other words, you have the directional derivative of the directional
Now,
derivative no matter
I'm
what
going
direction is
to
positive, that's
just
here,
work
which
with
means
this part in
you
here
have concave
from
up,
now
or
on
it's negative,
because
which means you have concave
b
down.
squared is there.
So
It's
let's look
always
back and see
positive
what would be the
because
deciding,
it's squared. How would we
and what
determine
I'm
it?
wanting to
Well,
be
look,
concerned about is
the
the
coefficient
signs,
here.
positive or negative.
If
So going
f
forward,
xx
I'm just going to ignore
if
this b
this
squared and just focus
is
in on
positive,
the inside here.
then we
Now,
have
if you
concave
think
up.
about it, this is a lot like a quadratic
And
function
we're
here.
looking at a minimum.
Notice we have a t squared
Now,
plus
so
b.
we're
t
assuming that we're
plus
plugging
c.
in
You could think of it
a
that way,
critical
right?
point.
Where a is
We're assuming we're
fxx
plugging in a critical
and
point.
b is
Just
2
like before in Cal 1
xy,
when we had the second derivative,
and
we
then
plugged
you
in a
had
critical
the
number.
constant on the end.
Well, now
So
we're
it's
plugging in
kind
a
of like
critical
that.
point.
And
Now,
we're saying that
I'm going to find the discriminant.
remember,
That would
it's
mean
b
if this
squared minus
happens, if this part here
4ac.
happens,
So,
that means
so
we have
let's think
concave
about this
up,
b
which
squared.
indicates
That's
we're
going
at
to
a
be
minimum.
4
Now over here,
f
this would
x
happen
y
if
squared.
if this is less
See,
than
that's b
0,
squared. That's this
which would mean concave
minus
down
4ac
at that critical point, which would mean we have a max.
Okay.
There it is.
So now I've got b squared minus 4ac.
That's what that would
now,
mean.
Let's start playing the game with this that we
Okay.
did with the discriminant
Now,
on the quadratic.
let's look at the next part.
And
Okay, so
that's
remember,
if
this
it's
is
less
the
than
part
0.
that would
So
be under the
so
radical.
less
And
less
we
than
want to say,
0,
okay,
and
what happens
fxx
if
greater
this
than
thing
0
is
then
negative?
that means you have
Let's
a
think about
minimum
what
at that
happens
critical
if this
point.
is negative.
Now,
If
I've got these
the
forals on here,
f
which I don't care
double
for.
prime,
So let me
I
just
mean
divide
f
them out.
xx is
And
less
what
than
I'm
0,
looking at
means you
is
have concave down, which corresponds to a
fxy
maximum.
now
Squared
let's look a little
minus
further.
f.
Let's suppose that
fyy.
okay,
So I divided out
let
that
me
4.
rewrite it up here.
Just makes it a little simpler.
If that right there is
so I'm
negative,
just going to
now remember, this
just
is
bring this
measuring the
thing forward.
concavity. This is measuring
Okay.
the concavity.
So we have f xy.
So let's think about what that means. That means
squared minus
that you have a
f
situation
x
like
x
this,
f y
because
there's
now
no
let's suppose
real
that's greater
roots.
than 0.
So
Or
before
you
we
have a
had
situation
less than 0
like this here.
and you see what that gave us.
Yeah,
Okay.
you have
Now,
one of those
let's suppose
two.
it's greater than 0.
In
Well,
other
that
words,
means we
you
have something like
the
this.
directional derivative of the directional derivative,
Okay.
no matter what direction
We
is
have a
positive.
graph that looks like
here,
that.
which means
you have
Or
concave up,
like
or
this.
it's negative, which means you have concave down.
Now remember, we're talking about concavity, so we're looking
let's
for
look
where
back
the
and see what
second
would be the
derivative is either
deciding
positive or
how would we
negative.
determine it?
Well,
Well, here
the
it's
coefficient
both.
here. We
If
have
f
positive up
xx
here
if this
and negative down here.
is
Over
positive,
here we have positive up here and negative down
then we
here.
have concave up.
So apparently the situation we have here is that
the concavity
and
changes.
we're looking at a minimum.
Okay.
Now this would
so
correspond to a saddle point.
We're assuming
in a
that
situation like
plugging
this, what
in
you have is
a critical
saddle.
point.
We're
A saddle
assuming we're
point.
plugging in a critical
In other
point.
words, that
just
point
like
we
before
found by
in Cal 1 when
setting
we had
the
the
second
first
derivative, we
partial
plugged in a
and the
critical
second,
number,
and the
well, now we're
partial with
plugging in a
respect to
critical
x
point
equaling 0 and the partial with respect
and
to y
we're
equaling 0,
saying that
and finding that critical point.
that would
That
mean
point
if this happens, if
is
this part here happens,
a
that means
saddle
we have
point.
concave up, which indicates we're
Now
at
we'll
a
look at
minimum.
an example of a saddle
Now over
point
here
in just a second.
this would
but
happen.
let's look at the other
if
case.
this
Let's
is
suppose
less than 0,
that
which
we
would mean
have
concave down.
this thing
At that critical point,
which would mean we have a
XY
max.
here.
Sorry.
That's what that would mean. Okay. Now,
let's suppose
let's look at the
this
next
is
part.
equal to
Okay,
0.
so that's if
suppose
it's
we have
less than
that
0.
situation.
So less than 0
Well,
and f
then
XX
the test
greater than 0.
we don't know what.
Then that means
we don't know what's going on
you have a
because
minimum
we
at that
could either have
critical
something
point.
like this, or
If
we could have
f
something like this.
double prime.
So
f
really,
XX is less than
if you
0.
have the
means you have
discriminant
down,
is
which
equal to
corresponds to a
0,
maximum. Now
you can't
let's look
tell
a little
much
further
from
Let's
this
suppose
second partials
that
test. Okay, so the test is inconclusive
rewrite it up
because the
here.
discriminant is 0.
Now let me show you
I'm just
something
going
here.
to just
to
bring
transition
this
over.
thing
We
forward.
were doing this. We were
Okay,
saying
so we have
fxy
squared minus fxx
squared
minus
fx,
and we were looking
f
you know,
y.
we said
Now
we
let's
started
suppose
off saying
that's greater
okay,
than 0.
so before
We looked
we
at
had
the options
less than 0,
and we said when this happens
here,
and you see what that
and
gave us,
we can determine
Now,
if it's
let's
concave
suppose
up
it's
or
greater than
concave
0.
down. Well, that
depending on
means we
f
have something like
XX.
this.
Okay.
In a lot of
We have a
textbooks,
graph
they
that
don't
looks
have
like
it
that.
written this way.
What
Or
they'll do is
like
they
this.
change it. And I presented it this way
Now
because
remember,
I think
we're
it's more
talking about
intuitive.
concavity, so we're looking
but
for where the
what they'll
second
do a lot of
derivative
times
is
either
multiplied through
positive
by negative
or negative.
Well,
And
here
you
it's
have
both.
this.
We have positive up here and negative down here.
And you have to flip the
over here we
inequality
have
direction.
positive up here and negative down here.
So then
So apparently,
this is the way
the situation we
the
have here
discriminant
is
presented
that
to you.
the concavity changes.
So what they'll say, so this is D.
so
Okay.
so D is
Now,
equal to
this
would correspond to a saddle point. So in a situation
And
like
what they'll
this, what
say
you have
is this:
a saddle,
if D
a saddle
is
point.
greater than
In other words,
0,
that point we
if
found
that
by
happens,
setting the first
and
partial and the second and the
if
partial with respect to x equaling 0 and the partial with respect
at that
to y
critical
equaling
number,
0,
let's say,
and finding that
critical
point is this.
that point
If this happens,
is a saddle
then
point.
you have
A
now
relative
we'll look
minimum.
at an example of a saddle point
So this
here in just a
corresponds
second.
to a
But let's look
minimum.
at the other
Now,
case.
on the
Let's
other hand,
suppose if that
this is greater than
we
0
have
and
this thing
fxx at this point.
Whoops,
This is greater than
xy
0.
here.
I didn't put that down.
Sorry.
And this is less than 0.
Then you have a max. Now the other thing.
Let's suppose that
so
this
so
is
let's go the
equal
other
to
way
0.
now. Let's suppose
we have that
D
situation.
less than 0.
Well,
then the test.
if this happens,
we don't
then you
know
have a
what.
saddle point.
We don't know what's going on because we could either have something like this,
A saddle
or
point.
we could have something like this.
So
And
really,
if D is equal to 0,
if you
the
have
test is
the
inconclusive.
discriminant is equal to 0.
So what I've done there is I've just
can't
split the inequalities.
tell
but
much from
the
this
thing is, I
second
wanted you to get
partials
the
test.
intuition of what was going on, and so I
Okay,
kept
so the
that
test
with
is
the discriminant.
inconclusive because the
Now let's
discriminant
look at some
is 0.
examples.
Of
Now
the
let
cases here.
me show you something here. Just I think
to
the
transition over. We
main
were we were doing
surface
this.
that
We
we
were
need to
saying
look at
fxy
would be a
squared
saddle.
minus
So let's suppose we
fxx
have this function
fxy.
f of x, y
And we were
equals y squared
looking,
minus x squared.
and we
Now
said
we
the
started off
critical
saying,
point
okay,
here is 0,
we
0.
looked at the
And you can find
options
that
and we
by
said
setting
when
the
this
partial with
happens
respect to x equals 0, and
and
of course you get 0,
we
partial
can
with respect to
determine
y
if
equals
it's
0, and
concave
you
up or
get
concave
0.
down,
But look at
depending
this
on
surface.
fxx.
Now, remember, our critical
In
point
a
is
lot of
right here
textbooks, they
at
don't have
0,
it
0,
written this way.
right there.
What they'll do is they change it.
And I
And
presented it this way because
that's
I think it's
clearly
more
concave
intuitive.
up, right?
Or
But what they'll do
okay,
a lot of
that
times
looks
is
concave
multiply
up.
through by a
Let me
negative.
put a plane,
And
a plane over
you have
here,
this.
and just to at x equals 0, and you can see there's some
And you have
concavity
to
up
flip
right
the
there.
inequality
Okay,
direction.
so case closed, right?
No,
So
look
then
at this.
let me just
This
rotate
is
the
the way
graph
the
around.
discriminant is presented to you.
Okay, so
And
what they'll
now let's
say,
look at it.
so this is D.
Okay.
So now
So
you can
D is
see it's
equal
clearly
to
concave
this thing.
down. So we had concave up and we had concave down.
And what they'll say is this:
So
if D
that's
is
the
greater than
example 0.
of where I
If
said,
that happens,
when
okay,
we look back at our
and
if
when we
f
look back at our graph here, we had
xx
these situations.
at that critical
This
number,
and
let's
this.
say the critical
So
point is
when that
this.
happens,
If
you
this
have
happens,
a saddle point.
then you have
Yeah. Now, of
a relative
course,
minimum.
there you all
Okay,
know
so
of
this
examples where
corresponds
you
to a
have
minimum.
concave down and
Now, on
concave
the
up,
other hand,
but it's the
if
saddle point
this
that
is
was
greater than
probably
0
that's the one I
and
wanted to show. So
fxx at this point, whoops, this is greater than 0. I didn't put that down. And this is less than 0. Then you have a max. Now, the other thing, so let's go the other way now. Let's suppose D less than 0. Okay. If this happens, then you have a saddle point. A saddle point. Okay. And if D is equal to 0, the test is inconclusive. So what I've done there is I've just flipped the inequalities, but the thing is I wanted you to get the intuition of what was going on, and so I kept that with the discriminant. Now let's look at some examples of the cases here. I think the main surface that we need to look at would be a saddle. So let's suppose we have this function f of x y equals y squared minus x squared. And now the critical point here is 0, 0. And you can find that by setting the partial with respect to x equals 0. And of course you get 0. Partial with respect to y equals 0. And you get 0. But look at this surface. Now, remember our critical point is right here at 0, 0. Right there. And that's clearly concave up, right? Okay, that looks concave up. Let me put a plane, a plane over here, and just to at x equals 0, and you can see there's some concavity up right there. Okay, so case closed, right? No, look at this. Let me just rotate the graph around, and now let's look at it. Okay, now you can see it's clearly concave down. So we had concave up and we had concave down. So that's the example of where I said, when we look back at our graph here, we had these situations, this and this. So when that happens, you have a saddle point. Yeah. Now, of course, you all know of examples where you have concave down and concave up, but it's the saddle point that's the one I wanted to show. So